In this video, we're going to talk about the start of probability. So first up, before we talk about probability, let's focus on some vocabulary that the IB uses. An experiment is going to be a process by which we obtain an outcome. Trials are going to be repeated experiments. The outcome is going to be the result of that experiment itself. And then we're going to talk about an event, which is an outcome from an experiment or a set of outcomes. And finally, sample space, which is going to be denoted by U. This is going to be all the possible outcomes for a given experiment, and it can be written as a list, or it can be in a graph, or it can be in a table. And we usually use this notation of N capital U to refer to the number of all possible outcomes. So if we think about this vocabulary in context, and we have the event that we are rolling a dice, well, if the event that we're rolling a dice, we're going to have the experiment, right, is the process by which we obtain. So we're rolling a dice. Trial is going to be how many times we roll the dice. The outcome, well, our possible results are going to be 1, 2, 3, 4, 5, 6. And then our sample space is going to be all of those possible outcomes. And the number of sample space would be 6 in this case for a dice experiment. Okay, as we probably know by now, probability can tell us the chance that something is going to happen. So probability is going to be a number that we can either write as a decimal or as a fraction or even as a percentage, and it can never be bigger than 1 or 100%, and never smaller than 0. We're going to be using the notation capital P. In brackets, we're going to have a letter, and this letter is going to talk about the event. So what is the probability of getting a 6 for our dice example? So there are two types of probability. The first type of probability, theoretical, this is the probability that's going to be on your exams. So this is the probability that is calculated mathematically. While experimental probability, that's when you actually conduct an experiment yourself and you record what happened. So you record how many times you rolled a 6, for example. This is something that you're probably going to be doing when you do your IAs, but for now we're going to concentrate on theoretical probability. And the probability of any event A is the number of outcomes that happen in that event divided by the total number of outcomes. And we'll do an example to understand this. For a normal 365-day year, find the theoretical probability that a person has a birthday in August, assuming that a person is equally likely to be born on any day of the year. So the first thing we need to realize is that our event is being born in August. So being born in August, we first have to remember how many days there are in August. There are actually 31 days in August. So the probability of being born in August, 31 represents the number in this particular event, August, and we divide that by the total number of outcomes, which is the number of days we have in a year. So we have 365. So this would be the probability that any given person is born in August. This next slide talks about our Venn diagrams, which is one way of representing all of our data set. And when we use Venn diagrams, we use what's called set notation. Now, set notation, these are these special characters that you see at the bottom. So it's going to be really important that we understand what these characters mean because they're going to be given to us in a question, and they're also given to us in the formula booklet. So first off, you're going to see that when we use Venn diagrams, it's always going to be inside a rectangle. This rectangle represents all of the possible outcomes for an event. Then you're going to see some circles. These circles represent the event that are happening. So when we have a circle and we have some numbers or some names inside, that means that it's happening in that event. Anything outside of this circle is not happening for that event. And that's what we call the complement of an event. So anything that is not in event A is called the complement of A, and we denote that with an A apostrophe. And when we're looking at a sample space that has only one event, A, for example, we add up the probability of A and we add up the probability of the complement of A. We're going to get that we have the full possibilities. So the full sample size is going to be represented here. The next important thing is the intersections. Now, the intersections is represented by this symbol here. This is when both A and B are happening. So A and B represents this kind of upside down U. And this is when we shade really the intersection of these two. The opposite of this is the union. The union is going to be when either or is happening. It could be just A, it could be just B, or it could be both of them. And we need to remember the difference between these two U's. I like to remember this one since it's union, which is absolutely everything. Well, this U here kind of represents the U of union. While this upside down U, I kind of see it as my N. So it's and. So this N for and is this U here. So that's how I differentiate both of these. Let's look at this example. In a group of 30 students, 17 play computer games and 10 play board games and 9 play neither. Draw a Venn diagram to show this information. Okay, so first step, 30 is our total. So when I add up all the numbers I see in this rectangle, I should be getting 30. The first number that we can put directly on our Venn diagram is 9. 9 play neither. So 9 is going to be outside of my two events. My two events will be computer games and board games. Now, if we look at the other information given, we have 17 play computer games. That means that there's 17 inside all of the computer games. So this big circle should be 17, while there's 10 who play board games. Now that means that's inside of this circle. Notice that this intersection is actually calculated twice when we look at the 17 and the 10. So we need to figure out first, what is this intersection? And then we'll figure out how many just play computer games, but not board games, and the other side. So I'm going to call this intersection X. I don't know what this is. So we're going to try and figure out what this is. If the intersection is X, then we can talk about this part here in green, which is going to be the people who play computer games, but not board games. Well, we know that all of the green is 17. And if we say that in this intersection there's X people, well, that means that the rest of this is going to be 17 minus this X. So remembering that this section, we're only looking at computer games, but not board games. And then we can do the same thing for the board game side. So the people who just play board games but not computer games, that's going to be our 10 minus X. Okay, so now we have some numbers and expressions on our sheet of paper. We know that adding up all the numbers in this rectangle should add up to 30. So we can create an equation for that. So this is the equation we create. 30, or sample space, is equal to adding up all the numbers we see. 17 minus x plus 10 minus x plus 9. We put all this into a calculator, numeric solve, and it's going to tell us that the value of x is equal to 6. So if the value of x is equal to 6, that means my intersection is 6. On the board side, I have 10 minus 6, so I'm going to have 4 people play only board games. And on the computer side, 11 people play computer games, but not board games. So now we did the first part, which is actually the hardest part, is creating this Venn diagram. Once it's created, then we can answer the rest of the questions. Part A, find the probability that a student chosen at random from this group plays board games. So we go and we look at that. So the probability of board game, that's going to be the total amount of people in the circle for board games. So adding up everything in the board game, we have 6 plus 4. So we have a total of 10 people out of a possibility of 30. Now you can keep it as 10 over 30, but it's easy to simplify this one. It becomes 1 over 3. And your calculator can simplify fractions for you. The next one is B. B says, find the probability that a student plays both computer and board games. So for this question, both, this requires the and, the intersection. So we look at where both of them are overlapping, and we see we have 6 out of a total of our sample space, so 6 out of 30. Again, when you put this into the calculator, you can simplify it to 1/5. And our last question, find the probability that a student plays board games but not computer games. So for this question, we go again in our circle for board games, and we see that in board games, we have 6 who play both boards and computer games, but only 4 of them play board games only. So probably that they play board games but not computer games, that's going to be our 4 out of our possibility of 30. And if you simplify this one, we're going to get 2 out of 15. So notice how this question was really, really useful to have a completed Venn diagram in order to answer it. And that's going to be what we're going to be doing for a lot of questions in this situation with 2 events. We're going to be building a Venn diagram first. Now we're going to go into a concept of combined events and compare that to mutually exclusive. Combined events simply means it's 2 events that do have an overlap, so they could be happening simultaneously at the same time. An example of that is looking at cards. Well, you could have a card that is king and hearts, right? So you could have the king of hearts, and then on one side you could have all the kings in the deck, and on the other side you could have all the hearts in the deck, and then you have your overlap. This is going to be the equation we're going to be using for combined events. What does it say? It's the probability of A union B. So the probability of both A and B happening is going to be the probability of A, so all the circle of A, plus the probability of B, all the circle of B, minus the overlap of these. Why do we subtract the overlap, the intersection? It's because when we added up the probability of A and B, we actually added up this section twice. So we're going to need to subtract it. This formula is given to you in the formula booklet. And we compare that to what's called mutually exclusive. If we have 2 events that are mutually exclusive, there's no overlap here, right? So they really have nothing that overlaps them, nothing that they have in common. So this could be, for example, tossing a coin, heads or tails. Well, you can't have both heads and tails in one toss, right? So this would be the formula for the union of A and B. It would literally be just A plus B. We don't have any intersection here. Let's do an example. A card is drawn at random from an ordinary pack of 52 cards. Find the probability that the card is a heart or a king. So to help you out here, I put all of the cards in a deck. We're looking for, find the probability that it's a card is a heart or a king. So let's look at how many are in each of these events. If we look at the hearts, which is the 3rd row here, we notice that there's 13 cards that are hearts, but there's only one of them that's the king of hearts. So 13, so 12 cards that are just hearts, and one of them, which is the king of hearts. If we look at the king column, so that's going to be this column here, we know that there's 4 kings in total, but one of them is the king of hearts, so the other just kings are in this section here. So with this Venn diagram, we can answer the question, find the probability that the card is a heart or a king. So heart or king, what we're doing, we could use the formula from the formula booklet. So using the formula, we get the probability of king. Well, we have 4 kings, plus the probability of heart, we have 13 hearts. Oops, sorry. Minus the intersection, we have one of these who are intersection. Now, notice that here I only use numbers. That's incorrect. I should be using my probabilities. So it's 4 out of a total of 52. It's 13 out of a total of 52, and it's 1 out of a total of 52. 52 and 52. So using the formula, since all the denominators are the same, we can add the numerators. So 4 plus 13 minus 1, we're going to get 16 possible cards here. Now notice that we could have done this also by simply adding the cards that we see here. So we could either use the formula, or we could look at our Venn diagram that we created, and we see the or means the union. So absolutely everything we see in our Venn diagram. So 12 plus 1 plus 13, that would be our 16. And that would be out of our total of our sample space, which would be 52. So 2 ways of doing this question: our Venn diagram or using the formula. Another important concept, and the last one for this video, is going to be talking about independent events compared to dependent events. So we say that two events are independent if they don't affect each other. The probability of A and B will be the probability of A multiplied by the probability of B. An example of an independent event is when you are picking balls from a bag, and every time you pick a ball, you put the ball back in the bag and you try and pick again. So that would be an independent event. On the other hand, we have dependent events, and this is where you have the probability of something happening, which is dependent of what just happened before. And the formula we have in the formula booklet for this is the probability of A given B has happened is equal to the probability of A and B divided by the probability of B. And we'll be doing examples to understand these formulas given to you in the formula booklet. The first example is, there are 60 executives attending a regional conference in South Africa. The Venn diagram below shows those who do some business in Angola or those who are in Mozambique. Find the probability that one of the people has done business in Mozambique, given that they have not done business in Angola. So first, let's use the formula in order to do this, and then we'll just use our Venn diagram. So find the probability that one of them has done business in Mozambique, given that they have not done business in Angola. So that means the not is our complement of A. And every time you see this keyword, given that, this should automatically link us that we're doing conditional probability, and we have the formula in the formula booklet. Okay, so first off, probability of M and not A. So this means it's the intersection of what's happening. M is this circle here, and then not A is everything outside of the red circle. So the only overlap they have is going to be this 18. So we're going to have 18 out of the probability of not A. Well, not A means everything in A has to go, but we can add up all the other numbers we see. So we have the 18 plus the 24, which is 42. So this is how we would do it using the formula from the formula booklet. Another way we could have done this is simply by looking at our Venn diagram. So we're told that we are given that the person was not in Angola. So automatically, if the person is not in Angola, that means that these options are out. And then we're told that we want a probability that they're in Mozambique. So we can see, okay, out of all the numbers that are left on the Venn diagram, this is the only one that's from Mozambique. And then we divide by the total sample space that was left, which was our 42. So kind of 2 ways of doing this. The formula from the formula booklet, and if you have a Venn diagram, you reduce your sample space to start with. So I removed the numbers that were not in the new sample space, and then you look at the number of outcomes. And the last question for this video, let's say A and B are independent events such that the probability of A is equal to the probability of B, and we say that this probably is equal to p. And they're telling us that this probably is not equal to 0. So there is a probability here. It's a number. Show that the probability of the union of A and B is equal to this. Now, in order to do this question, we need to remind ourselves of the formula for independent events. And I'm going to write down the formula for independent events. So from the formula booklet, we have two important formulas we need to look at. Independent events, we're told that the intersection of independent events is multiplying the events together. And then the other formula we need to look at is the probability of any union of combined events, and that's the probability of A plus the probability B minus the probability of their intersection. So for part A here, they're asking us to show that the probability of A union B is equal to this. Well, when we do a show that question in the IB, we cannot start with the answer. So I need to work with this in order to get this answer here. So I can use the fact that I have this red equation from the formula booklet. And I know the probability of A is equal to P, and that's the same as the probability of B. Now, I need to subtract this by the probability of the intersection of A and B. Well, since I have independent events, the probability of A is P, and the probability of B is P. So now I have P times P here. By simplifying this a little bit, I can add my two p's, and then p times p, that is just p squared. And that is in fact what they wanted us to show. So we're good for part A. For part B, find the probability of A given that A union B. And they ask us to simplify this. So a little bit of algebra here. So first, I'm going to take the probability of A given A union B, and I'm going to write this using the formula from the formula booklet. Okay, so this is the formula from the formula booklet, an adaptation. So whatever you see as the given that, this is the one on the bottom, and then it's the top part is the and. So it's A and this part. So let's try to understand what that top part is. So the probability of A is all of this happening, right? So all of this circle. The probability of A union B, this is absolutely everything. That's A or B, right? So all of this happening. And then when we're trying to take A and A union B, so we're looking at the red part and then and the intersection of the yellow part. Notice that that's just the probability of A happening. So the overlap between the red and the yellow, that's all the actual red. So that's the probability of A. So the top part can be simplified to the probability of A. And then we know that the probability of A is equal to P. So the top part is going to be simplified to P. And then what about the bottom part? The probability of A union B, well, we just did that, right? The probability of A union B was our 2P minus P squared. So that's going to stay here on our denominator. Now, they want us to simplify this. In order to simplify, this is one of the tricky parts of our algebra. We need to realize that in the denominator, we have two p's here. So I can factor out a p from the denominator, and I'll be left with 2 minus p. And then on the top, I still have my p. By factorizing out the p, now I can cross them out. And I'm going to be left with simply 1 divided by 2 minus p. And that's going to be our final simplified answer. So this question was a little bit challenging with understanding the concepts of independent events and using the formulas from the formula booklet, and then finding a little touch of algebra. So just for you to know, all of these formulas are given in the formula booklet, and now we're just going to practice a lot with these types of questions.